I am in Sillitoe working at UCL. I look after the CATH protein structure classification database. At UCL we take all the structures in the PDB, all the protein structures in the PDB, and we chop them up into domains. That's a protein domain. And with those domains, we then try and take all the protein domains that we think are related by evolution, so there's a good evidence that they're related by evolution, and we stick them all into the same superfamily. After doing that, if I show you this animation here, so what you're seeing here is that lots of different protein domains have a very similar structural core at the centre. And this can be going right the way through evolution to loads and loads and loads of different areas of life. And what we're interested in doing is trying to bring together the most conserved core to try and find information that's interesting right the way through evolution. Now, here, this is an extremely kind of complicated superfamily with lots and lots of diversity, functional diversity, sequence diversity, structural diversity. But if after a while the animation will just remove all of the bits that we think are less interesting, well, depending on how you look at it, and just look at this structural core, which is considered like an ancient structural core, which is like a fossil of a protein structure, which can help us to inherit lots of information from one protein structure to another protein structure. So why is this interesting to Bioges? Well, I am a user of Bioges modules and a contributor as well. So because we are tying protein sequence with protein structure and with protein function, so some of the Bioges modules that I am interested in using and contributing to are SEB's multiple sequence alignment. So the kind of families that we're talking about can have many thousands of sequences, and we're interested in mapping function annotations onto those. So one of the challenges that we were throwing in Seb's direction for his Google Summer of Code is being able to have multiple sequence alignment that can visualize and not fall over for those huge sequence alignments, something which he did very well, I might say. We're also interested in tying together lots of different components in terms of displaying structures, displaying functional site residues, mapping those to SNPs, and bringing together lots and lots of different data from lots of different data sources. I will stop there.
Okay, thank you. We have 2 minutes to make presentations. Yeah, none of any questions.
I have a question.
Yes, there's a question. Yeah?
Which tools are you using to determine these cores or bring the proteins together, like sequence alignment or structure alignment or human?
So that's a good question. So this CATH is based largely on manual curation. So, however, that's guided by automatic comparison algorithms. So these superpositions are generated by an automatic structure superposition, which actually only tries to superpose the most 95% most similar residues and leave the other 5% off. So if you do like a rigid body superposition and try to superpose everything, then it actually gets very messy. And what we're trying to do is just superpose the bits that we can see don't change. So this is automated. It's not yet on GitHub release. We're going through the licensing issues at the moment.
Did you guys develop the algorithm yourself, or is it?
Yeah, well, so my PI is Professor Christian Orengo, who co-developed the SAP algorithm, which is the one that does this. It has since been rewritten to do the multiple structural alignments, which is what this is based on. So, and that's the thing that we're trying to get out onto open source license.
Is there another question?
So, silly question. So is this JavaScript only, or?
So that is a movie made from PyMol, and that would. So I'm currently looking at the PV protein viewer visualization with JavaScript. That looks great so far. Obviously, I mean, PyMol struggles with when you have like that's 80 structures on the screen at once. So I need to find like the line at which things start to fall over, and that's a continual problem with everything that we do. In that, and I'm sure lots of people share it, that 80% of the time everything looks fine, but then 20% of the time stuff falls over, and we have to make sure that it works 100% of the time, ideally.